Hello again everybody! In today's video, we're going to talk about the law of conservation of momentum in two cases. The first is going to be in perfectly inelastic collisions, and the other is in perfectly elastic collisions. Let's get started. The law of conservation of momentum simply states that the total momentum in a system is constant. Well, what does that mean in math terms? Well, that just means that the initial momentum is equal to the final momentum of the entire system. So let's just say we were focusing on just the x-coordinate of a collision between some amount of particles. This is just going to be the momentum in the x direction initially is equal to the momentum in the x direction for the final part, or after the collision. And if we break this up even further, we'll just get the mass of the first particle with some initial velocity plus the mass of the second particle with some initial velocity plus yada yada yada, it really depends how many particles you have in the system, is equal to the mass of the first particle with its final velocity plus the mass of the second particle with the final velocity plus yada yada yada. Again, it depends on how many objects you have in the system. So the total momentum that we start with in this system has to equal with the final momentum that we get after every collision in the system. And there's two different collisions that we can have. We're going to talk about inelastic collisions first, and then we're going to go with elastic collisions. Let's start with inelastic collisions. In an inelastic collision, objects will stick to each other. And what I mean by that is if I have some mass 1 colliding with some other mass 2 with some initial velocity, once these two collide, we're just going to have a big old ball of m1 plus m2 going at some final velocity. And we would use the conservation of momentum to solve this. And of course m2 can have some velocity, but for this simple example, we're just going to say it's stationary. A semi-truck with mass m1 and a smaller car with mass m2 have an inelastic collision at an angle as shown below. What is the final velocity and angle they make, assuming that the cars travel to the right after the crash? Well, first things first, we have to split m1's velocity into their respective x and y coordinates so that we can pair those numbers with mass m2. Let's start with the x coordinates. I'm just going to fast forward a bit through the algebra, because of course the physics is the most important part, and then the algebra is just kind of time consuming, so we're just going to fast forward a bit. Okay, so for mass m1, it has a velocity v1 going down to the right, but this is actually just split up into their x and y coordinates that can make a right triangle, and of course we have it at some angle, so we can just use our handy dandy SOHCAHTOA to find out v1 cosine theta. And for Vy, we're going to have V1 sine theta. Okay, that's not so bad. Now let's do the momentum in the x direction. The momentum in the x direction is going to be the mass of the first truck times the velocity of the first truck times that cosine theta, because we are focusing on the x coordinate, minus m2 v2, and I specifically put a minus sign there because it is going to the left, not to the right, so therefore it gets a minus sign. That is equal to the combined masses of m1 plus m2, since this is an inelastic collision, times the final velocity in the x coordinate. If we just divide m1 plus m2 on both sides, we're going to get that the final velocity in the x direction is Okay, let's do this for the y-coordinate system now. The momentum in the y direction is going to be dignified by minus m1 v1 sine theta, and the minus sign is because for the mass of m1 it is going downward, so that deserves a negative sign. And the mass for m2, that's not going in any y direction, so just 0 there. That is equal to the combination of m1 plus m2, so of course it is an inelastic collision, times vfy. And solving for the final velocity in the y direction, now we have the final velocities in the x direction and the y direction, so we have one last step to solve for here. Now the problem said that we are assuming that the cars travel to the right, so we can just say that there is going to be some velocity to the right, dignified by what we solved for earlier. Then there is a downward direction, and the combination of these two is going to be our final velocity, v sub f. So this is using a right triangle, so we can use the Pythagorean theorem. Vf is equal to the square root of v final in the x direction squared plus v final squared in the y direction. One final step that we have to do is solve for our angle that it makes, and of course you can use SOHCAHTOA again, and figure out that this is going to be the tangent of theta is equal to And there you have it, our first inelastic collision example. Now let's move on to elastic collisions. In elastic collisions, we're going to have objects that will bounce off of each other. So for example, if we're playing billiard balls, we're going to have some mass 1 colliding with some other mass 2 at some initial velocity. Maybe we're going to have a situation where now mass 1 is bouncing off to the down and left direction, and mass m2 got some of that momentum and is now moving to the right. For elastic collisions, you are going to need to use two conservation equations. The first, of course, is going to be momentum. The momentum initially is going to equal the momentum final after the collisions, and you're going to need to use the conservation of energy. The kinetic energy initially is equal to the kinetic energy after the collision. And the reason why elastic collisions do conserve this energy is because all of this energy is being transferred into kinetic energy. Whereas with inelastic collisions, that energy is being transferred in other forms, whether it's thermal, sound, or material deformations. Let's look at an example. A car of mass 1689 kilograms collides head-on with a parked truck of mass 2000 kilograms. This collision will be elastic if the velocity of the truck is 17 kilometers per hour in the same direction as the car's initial velocity. After the collision, what was the initial speed of the car? Okay, first things first, let's just write down what we have. Let's just say that m1 is equal to that first car, 1689 kilograms. We're going to solve for the initial velocity for the first car, and that we don't know. We also don't know what the final velocity is, so that's also a question mark. For the mass of the second truck, that's going to be 2000 kilograms, and with its initial velocity at 0, and its final velocity at 17 kilometers per hour. Okay, well, let's start using some of these conservation equations, and let's see what we can do with them. Let's start off with the momentum. Now let's do the kinetic energy. Okay, we have both of our equations that we need to solve this problem. Now there are two ways of solving this problem. For this example, I'm going to solve for the final velocity of the first one, and then plug that back into the momentum. Or you can do the reverse, and solve for this final velocity of the first one, and plug that back into the energy equation. Both of these work out, and it's just a matter of choice. But I'm going to be honest with you guys, I was messing up for about 20 minutes to 30 minutes just because of a minus sign. So when you do this on your own, just be very careful of those minus signs and every other algebra. Alright, I'm going to blast through this at lightning speed just so we can finish the video. Alright, that took a long time, but here we are at our final result. Once we plug in all the numbers that we got from the initial problem, we're going to get 18.6 kilometers per hour. And holy moly, this question was insane, but hey, something as simple as a car crashes to another car causes this mathematical mess. But I hope that this video helped you guys out, and good luck in your physics classes. See ya later.